Let's recall what was the statement. Spectral. There are two versions. One was with a linear operator and the other was with a matrix. Let D be a Hermitian space. And let T from V to V be a linear operator, a normal linear operator. Okay. Then there exists an orthonormal basis of V made up of or consisting the eigenvectors of T. In matrix form, that would imply that if you have a normal matrix, it would be diagonalizable by an unitary matrix. Equivalently, if A is a normal matrix, then say A n cross n is a normal matrix, then there exists an unitary matrix P n cross n say such that P in P star is diagonal. Okay. So the proof of this is rather simple, as we'll see. Lemma 1. The question that we have already asked to group in is if P is an operator on a linear operator on a Hermitian space V does that. And W subspace of V, T and invariant subspace, T invariant subspace, that is T W is a subset of W, then W bar, that is the orthogonal complement of W, is T star invariant. That is T W star, T star, excuse me, T star W bar is a subset of W bar. And the proof of this was rather simple. Let's recall this anyway. So how did we show this? Suppose W is an element of W and let U be an element of W bar. Okay? Now TW is a subset of W. What does it mean? The T of this will again be inside W. And we are trying to show that T star W bar is an element of W. I mean, it is a subset of W bar. That will mean star u belongs here. So how could we show that? If we take t star u and take the product of that with w, if that is equal to 0, then we can immediately conclude that t star of u is in this one, in this w part. So consider that. Let's consider w t star u. Then, and note that this t was an arbitrary linear operator. It was not assumed to be normal or Hermitian or anything. It was just a linear operator. And we showed yesterday that this is then equal to t w u, right? Remember that this t w was a subset of w, right? So, I mean t w was t invariant. In particular, this t small w would be an element of w. Right? So this belongs to w, okay? And this u belongs to w part by definition. We have taken w part. So this is inside w part, right? And therefore, their inner product is equal to 0, right? Okay. So we see that w, the inner product of w and t star u is 0. That means, and w was an arbitrary element of w. So that means, if you take t star of any element of w part and take the product of that with w, you get 0. So that would immediately imply the claim. So this implies this one. This is true. T star of w part is a subset of w part. So that's the first lemma, and now the second one. Let T be a normal operator on a Hermitian space V. Then every eigenvector V of t corresponding to some eigenvalue lambda, say, eigenvalue lambda is also an eigenvalue, eigenvector of t star with corresponding to eigenvalue eigenvalue lambda bar. Okay. So we are assuming that t is normal, and we are going to show that if small v, well, we have not assumed, suppose small v is an eigenvector of t corresponding to lambda, then v is also an eigenvector of t star corresponding to lambda bar. The proof is simple. Can I wipe this part out? Number one. Thank you. So proof. Define this operator as t minus lambda I. And note that, well, we assume t to be normal, right? Consider this, a star s. We are trying to show that s is normal as well. Okay? And this is t minus lambda I star t minus lambda I. Is that a star is here, right? So that becomes t star minus
lambda
this one
lambda bar
I, right? lambda bar I times t minus lambda. That is t star t minus lambda bar t minus lambda t star plus lambda squared I. Right? Is the multiplication alright for? Okay. Now note that t star t is equal to t star, right? It was normal operator. So that is equal to t star minus lambda prime bar t, lambda t star plus lambda squared I, right? And then this just becomes t minus lambda I times t star minus lambda bar, that is S star. Okay. Right. This is, if you just multiply this, you will just see that this is t star, and then lambda t star is here, lambda bar t is here, and then the product of this is just this one. So indeed, you see that if you define it in this manner, it is a normal operator, right? So here, of course, I is the identity operator on the vector space. I hope it is clear from the notation. Yes, Vikram.
One question, not slightly related.
Yes.
But why this theory is called spectral theorem?
Well, the eigenvalues are kind of the spectrum of the matrix. You are having the entire matrix here, A, and then you are writing T star as some matrix where on the diagonal appears the eigenvalues. Okay? So it's like you are sending the white light through prism, and it is decomposing into fundamental colors. I think it's just an analogy for which this means. So this is a normal operator, that is clear, and now what we are going to do is that we'll continue that proof here. So I hope wiping out lemma 2 is fine for all of you. So we continue the proof from here. We have here that S is normal. So S star is equal to S star S. And now consider this. Let V be the eigenvector. Please have it quiet. Let V be the eigenvector of T. Corresponding to the eigenvalue lambda. That would mean that S of V is equal to T minus lambda I of V, which is equal to TV minus lambda V, and that is equal to 0, right? So V is an eigenvector of S as well, corresponding to the eigenvalue 0. Okay. It's sufficient to show that V is also an eigenvalue of S star with eigenvalue 0. So how do we show that? So SV equal to 0, that is if and only if, remember we are in a Hermitian space. Okay? So that means the product is positive definite, the inner product, right? The form, I mean. The form on this is positive definite. Now since this is a normal operator, we know something. SV, the product of these two, is equal to what? From the last class? A star B, A star B. Since it's normal, so you can take this on this side, so S star of B, and and then you switch that. S star is equal to A star S. So we'll get this one. And this is if and only if A star V is equal to 0. Right? Okay. Manish, it's fine. Ashwin? Alright. So this, yeah. Rishabh? U? Right? There is no U here. It's V. Okay, so it's V. Right. So A star V is equal to 0. That means that V is indeed an eigenvector of A star with eigenvalue 0. Right? Now what does it mean by A star V to be 0? That is T star minus lambda bar I of V, that is equal to 0, right? That is T star of V is equal to lambda bar V. Right? So we're done. That was the claim, right? So now we are in a good shape for proving the spectral theorem. Let's write this part out. Prove it here. Yes.
So how do we go from PV minus lambda v equals to 0 to the next level? The form is
So here,
no, PV minus lambda v equals to 0.
right?
From there we see that the form is 0 because
No. Here what we are saying that SV is equal to 0. S of SV is equal to 0, and that means if you take the inner product, that's also 0. And this is an if and only if condition because it's a positive definite.
Got it.
So now how do we prove the spectral theorem? Well, by very old technique called induction. So by induction. At first, for dimension V equal to 1, it's trivial, right? If dimension V is equal to 1, so suppose we have some operator, V to B, you take some basis, and you know that it's a Hermitian space. Okay? So you can normalize that. So for dimension V equal to 1, it's trivial. The claim or the assertion is trivial. Then let's assume now the induction step. So that was the step 1, basic step. Okay. Let's assume that it holds, or it also holds for all V with dimension V less than or equal to 1 for some n larger than or equal to 1. Okay. For 1 it's fine. Any doubt? For 1 it is actually trivial. Every matrix is diagonal in one dimension, right? And then suppose it holds for some n. We're going to show, so the claim is that the assertion also holds. Assertion means that the statement of the theorem also holds for dimension V equal to n plus 1. So let me wipe this part out and recall once more what was lemma 1, because we forgot to draw one corollary from there. Yes?
Why for V equals to n plus
That's the basis, right? And it's a Hermitian space. So that means it is positive, the form is positive definite. So you can normalize it, sure. And you get just some vector of length 1. That's your orthonormal basis.
But the eigenvectors part?
Well, take any eigenvector of T.
Okay.
Eigenvectors are by definition non-zero things. Eigenvalue could be 0, but not the eigenvector.
Oh.
So lemma 1 again, just recall it because we are going to use it immediately. So what was lemma 1? If TW is subspace of W, then T star W parts is a subset of W part, right? Now a corollary from there, or an equivalent statement actually, is that if T star W is a subspace of W, then T W, what can you tell about that? Oh, wait a minute. T W part, yes.
Subset of W.
W part. You are just changing the roles of T and T star. Yeah? Yeah, sure. So suppose you take some eigenvector of T, and suppose V is of dimension 1. So an eigenvector of T is by definition a non-zero thing. And then the form on V is positive definite. Positive definite form. So if you are taking an inner product of a vector with itself with respect to a positive definite form, and if that vector is non-zero, then the product is not equal to 0. Right? So in particular, you can divide with the, well, at first, it's positive definite, so it's a positive quantity. You can take a square root and normalize, divide by that. Okay? So Riti 1, if it is negative definite, it's not possible to normalize in this manner, right? Because you cannot extend the square root. So you can normalize, and once you normalize, you get a vector of length 1. Okay? And that's your orthonormal basis because it's of dimension 1. And suppose now that it holds for some n, here we'll go one dimension more. And there we are going to use this corollary. So now we continue this proof after we recall the lemma and the corollary. Let V0 be an eigenvector of T, and let W be defined as a span of V0. Okay? Then, well, since it's an eigenvector of T, we know something. It's an eigenvector of T star as well, right? We just showed that. That is, if it is a normal operator, if you have an eigenvector of a normal operator, it is also an eigenvector of T star. If it is an eigenvector of T, it's an eigenvector of T star with eigenvalue lambda bar. So then, P0 is an eigenvector of T star, and what does this imply? That T star of W, so V0 is an eigenvector of T star. That means the span, what is span of V0? Is a line passing through the origin of V0. And since it's an eigenvector of T star, that means that if you apply T star on V0 or on the span, you do not go away from this line. You remain in the span. In particular, the span is invariant under T star. Okay? So that implies T star of W is inside W, is a subspace of W. Okay? Now we apply this. So if T star of W is a subspace of W, that would mean that W part is invariant under T.
Yes.
Okay? T of W part is a subspace of W part. Right? Now what is the dimension of W part? N minus 1, because it's a non-degenerate form, it's a positive field form. It's non-degenerate of the entire space. Right, it's n plus 1, right. So we go one dimension less. So the dimension of W part would be n. Okay? So let's now clear up some space. Maybe lemma 1, because let the proof be there. So and also the corollary. So we continue up here with the star notation for dual or adjoint, whatever you take this. No, nothing. This is just, we're going from there to there. So TW part is inside W. That means T from W part to W part is again a normal operator on a Hermitian space, right? Because if you restrict the form to W part, you are restricting the same form to some space of dimension 1 less. Is normal operator on the Hermitian space W part, and dimension of W part is equal to n.
And by induction hypothesis, we already know this.
Know that there exists an orthonormal basis of W part. So what you do now? That implies there exists an orthonormal basis say W1 dot Wn of W part, made up of eigenvectors of the eigenvectors of T. So we are just one step away from the end of the proof. We have to extend this basis somehow. Okay? Yeah, right?
No, just Ramschmidt orthonormalization.
Yes, we are doing something like ground speed, of course, because we want to add some element with that, and so that the basis remains orthonormal. Okay?
So we add an element which is not in the span of those.
Right. So we
W1.
know already that it is perpendicular on V0. Should we just add V0? Normalize it and add. Define W0 to be V0 by its norm. Okay? It's a non-zero vector. So norm of V0 is not equal to 0. It's an eigenvector, right? By definition, it is not equal to 0. Okay? So define this and let V be defined as W0, W1, Wn. Then V is an orthonormal basis see, the proof of spectral theorem is not that difficult given the lemmas that we already have. Now, what's the use of this?
How do we know that D0 is orthogonal to the rest of the things?
The rest of the things? Okay. What are these things? W1 to Wn.
The orthogonal basis of double quad.
Right. And what is D0? A basis of W. So you are taking some element which is in the basis of W and combining, which is an orthonormal basis of, this is an orthonormal basis of W, right? It's normalized. Okay. And you are combining it with an orthonormal basis of W part.
Oh.
You already got this perpendicular, that is W0 is perpendicular on this one, this one, this one, this one, because this is in W and those are in W part. Okay, so why do we use this spectral theorem? I think you have all used this at some point in your life. Yes, exactly. You have taken pictures, right? And then you have uploaded in WhatsApp or perhaps you are filling up a form, and then you had some picture which has to be reduced to some size less than 2 MB. Okay. So what did your software or WhatsApp, what did it do? Yes, exactly. How does it reduce the pixel sizes? It applies spectral theorem, but nevertheless your picture, which may not be symmetric, right? So if I take a picture of you, then you are sitting here and Rithiman is sitting there, and you and Rithiman do not look alike, right? So it's not a symmetric matrix. The picture, it doesn't. It is not representing a symmetric matrix. So what do we do? How do we apply this theorem that we have just proved?
But each individual pixel is.
No, we take A transpose. So A is a matrix. You take the transpose of that, multiply it,
That's always
or A transpose A, and that's a symmetric matrix. You know something more about that. How would their eigenvalues? Well, it's symmetric, and you can say something about the eigenvalues. What is that? They're real. And how would the signs?
Positive.
They will be positive. Why? Okay, let's check. You are having A transpose A, right? And suppose V is an eigenvector, so that is equal to lambda V. We want to show that lambda should be positive. What should we do? Wonderful, yes. To multiply with the transpose of V. And there you get this. What is V transpose V? Yes, right, the norm. Okay. And here you are having what? AV, well, you are making here AV, the norm squared as well. So you know already that this is greater than equal to 0, this is greater than equal to 0, lambda has to be non-negative. So you know something, that is if you take A transpose A, the eigenvalues are going to be non-negative reals. In particular, you can take square roots. And square roots of these things are called singular values of the matrix A. You will later learn about singular value decomposition or principal component analysis. They are very important things in analyzing data or image quality. So what you do, you get the square roots, and then you take the huge ones and throw away the negligible ones. Okay? That's how you reduce the size. The size of a size of a data or size of a picture. You reduce it in this manner. That is, you organize the positive square roots of these eigenvalues and take only the huge ones, the largest ones. Okay? Throw out the rest of the things. That's called actually dimensionality reduction. We will learn this later in more detail. Is there a class now?
Yes, sir.
Alright. So then we end here. Wait a minute. About the Cauchy-Schwarz thing, actually last time we said that just take the dot product, but actually, it's rather obvious if you just you are considering a vector space V, a Hermitian space V, it has an orthogonal basis, right? So if you take the coordinates of V and W with respect to that orthogonal basis, this just becomes X transpose Y, right? Because with respect to the orthogonal basis, the Gram matrix is identical. And you can directly go from here by use Cauchy theorem. Another way to see this is that suppose you have these two vectors U and V, and then we said that the projection would be just, this projection would be U V by V V V, right? So this is the length of this part from here to here, and this one would be just U minus this one. So in particular, that would mean that the norm. So it's a right-angled triangle, and the length of the hypotenuse is larger than the length of any other side, right? So you have this squared, that is the length of U squared, is larger than, what is this? U V squared by norm V squared. You have the Cauchy theorem immediately from here. And if you want to get it algebraically, you can subtract this one from U. So you get U minus, if you do not want to look at the picture and deduce immediately from there, you can also take this and take the norm of this. And remember that you are in a Hermitian space. So this squared is greater than or equal to 0. Simplify this, you will get Cauchy theorem. So there's plenty of ways of proving Cauchy theorem using the commutative inner product spaces. So that's all. Wish you all the best for the exam, and come to the Friday tutorial. The things that I plan to do as an application of spectral theorem, I will just upload.